Short tutorial on BGP multi-homing techniques. You'll have to excuse me because I've got a very bad cold, so I'll probably run off coughing and spluttering somewhere while I'm giving this talk, but just try and bear with me as we go through that. My name is Philip Smith, work for Cisco Systems. I live in Australia. Most of my work is in the Asia-Pacific region. I thought I'd come and offer this tutorial to you to see some of the things that we're trying to teach people in the Asia-Pac region to be a bit more efficient with how they connect to the internet or how they connect their customer ISPs to the internet. This presentation has got a lot of slides, but because most of it are just a lot of examples, configuration examples, and so forth. If you want to follow the presentation, the slides are up here already. So if you go to this web page, you get the slides from this presentation. I think if you came to Barry's one before dinner this evening, his slides are also up there. And if you went to Alvaro's one in the afternoon, they're also up under there. Okay, it's a big PDF file. Feel free to follow it. I guess at some stage the slides will appear on the NANOG website as well. So I'm taking a bit of a guess that they'll actually appear under that URL. Is it? Okay. Great. Okay. I checked a couple of days ago, so.
Oh, no, I make it wait till you're ready.
Great. Okay, so slides are there if you would like to follow them through this. Now, as I was saying, this presentation has got many configuration examples, so it's really aimed at, if you're trying to figure out how to get started doing multi-homing, you can take these slides, the configuration examples in there, and try and custom or massage them to fit into your particular situation. Use a Cisco IRS CLI, because that's all I know. It's aimed at service providers. The techniques can be used by many enterprises as well, but quite often after these sorts of presentations, I get people saying, oh, well, but what about my little customer with his Class C? How do I multi-home him? And I don't really go into that because that's kind of a current thorny topic. So it's aimed at service providers who've got, delegated address space from the regional registries. This presentation, if you want to ask questions while I speak, feel free to do that. Right. What I'm going to cover, basically these 6 things. I'm going to skip through the first 3 fairly quickly. This is more just setting the scene, how I'm defining things. I'm just looking at some simple cases, how you connect to the same ISP and how you connect to different ISPs. The final 3 bits are the more interesting points of the presentation. That seems more what people are facing these days and how to connect to the internet. So, first one. How multi-homing is defined? Well, I think the best definition really is you've got more than one link external to the local network. Now, that's either going to the same ISP or to different ISPs. You can multi-home to the same ISP quite easily, either to the same point of presence or to different points of presence across the network. You usually have 2 external-facing routers. And some people multi-home with only one external-facing router. And to be honest, I think that's just a bit silly. If you're going to go to the expense of connecting to 2 ISPs or have 2 links to your upstream, you should have 2 routers. That also gives you router redundancy as well. You need an autonomous system number. You're going to be using BGP, and to use BGP, you need an AS number. You obtain that from your upstream ISP, or you get it from the regional registry. I'd guess in most of your cases, it would be from ARIN. Fill up the forms, they'll give you one in however long it takes. Okay. Now, again, to try and keep this simple, one theme through a whole presentation is I'm aiming for simplicity. So rather than get really bogged down on all the different fancy things you can do in the configuration, we're going to stick to these 3. We're going to use prefix lists to filter prefixes. We're going to use filter lists to filter autonomous system numbers. And we're going to use route maps to apply policy. You can use route maps to do all sorts of things, but to keep life simple, I'm assuming we're beginner, intermediate, learning how to multi-home and so forth. We stick to this. and it really makes life a lot easier. The policy tools that we have, just a reminder, local preference is used for outbound traffic flows. Metric is used to determine inbound traffic flows, gives you a local scope, in other words, between you and your neighboring autonomous system. You can use ASPath prepend to determine inbound traffic flows, but that's internet scope. Use ASPath prepend, the whole internet will see what you've done. And finally, we use communities to go into more specific inter-provider peering situations. Again, later on in the presentation, you'll see examples of communities being used. Basic assumptions: must announce the assigned address block to the internet. It's amazing how many ISPs don't do this. But certainly in my region, if you look at APNIC's terms and conditions of membership, they say you should announce your allocated address block to the internet. Okay? There's a lot of people just say, ooh, wow, I've got my 32 Class Cs from APNIC, and they announce them as that. Right? So try not to do this. May also announce sub-prefixes, but with that, reachability is not guaranteed. Well, in fact, nothing is guaranteed on the internet, but it's more than likely the longer the prefix, the less likely it is to be visible across the internet. The regional registry minimum allocation is a /20 these days across all three registries. Several ISPs will actually filter the registry blocks on this boundary. Some people call it the net police filters, other people call it other things, but this is the current one I picked off. I think it was one of the European mailing lists. I picked this one off and updated it. But it's got the three registries. These are APNIX blocks, ARINS blocks, and the RIPE NCC blocks. And they basically allow prefix sizes from /9 through /20. Anything announced to the internet outside those ranges gets dropped. Now, I'm not saying that using NetPolice is a good idea. Some people say it's designed to punish ISPs who pollute the routing table, rather than, they don't announce aggregates, they announce specifics. This is to encourage them to be good citizens. But certainly where I come from, it impacts legitimate multi-homing. And regions where the domestic backbone is unavailable or costs a fortune. Australia and India are the two big examples where international circuits are cheap compared with getting any capacity domestic. It's also, well, I would say it's reasonably hard to maintain. Generally when I go and visit people and they say, oh, well, I put this in, I discovered it on a mailing list, it's about, a year out of date, they don't have the registry's most recent allocations in there. So you really have, if you're going to do this type of filtering, you must keep it up to date. Right? So watch the NANOG, whichever mailing lists. All the registries announce when they get new blocks. You need to keep these filters current. Right. So the different multi-homing scenarios we've got. Well, the first one is a stub network. In this case, your network's out here. Your router is connecting, say, 2 or more parallel links to your upstream. You don't need BGP for this. Right? There's no need to go into the complexity. In this router, you simply point static default to your upstream, and that's it. It's as though you've got one connection. Right? So there's no need for BGP here. And in fact, if you apply to the registry for an AS number for this, they'll tend to send you packing. This one, again, you're only connecting to your upstream ISP. You're connecting to different sites or different routers of your upstream. You should use BGP for this, but there's no need for a public AS number. Right? You're only connecting to your upstream, so you're hidden behind the upstream. Use a private AS. There are 1,023 of them, so there's plenty of scope there. And again, your upstream ISP just announces your address space as though it was a static connection to the network. We've got some examples of these coming up. And this situation is the more common one. Your AS100, you can connect all sorts of ways from the internet, and a first-timer seeing this finds it a bit intimidating to actually set all this up properly. Now, the multiple sessions to a single ISP, we just clear these away quickly. You can use something like eBGP multi-hop. You run BGP between loopback interfaces on the routers. and that will let you load share over the circuits between the routers. So in this case, I've got 3 links. Right, so I just point a static route for the loopback interface on this router. Just point it to each of the serial interfaces on this one, and then I just do the BGP to the loopback interface on the AS200 router, as simply as that. This is a common way of using BGP to load share over 3 parallel circuits. There's another way of doing it. You can use this thing called BGP multipath. So rather than setting up the static routes pointing to the serial interfaces, you just simply set up 3 BGP sessions and have this directive maximum path 3, which will install 3 entries in the routing table to get to the remote router. Depends on which version of iOS, but you have a limit of 6 parallel paths or so. There's a downside with this. Carrying the full routing table seems to be fashionable these days, and having 3 external feeds of the routing table means a lot of memory. So people don't really like this one if it means dragging down 110,000 prefixes on each link. Okay, so I tend to find that people are heading back towards using the eBGP multi-hop system, where you've got 1 BGP session load shared over the 3 circuits. This is actually the best way of trying to do any multi-homing. You have 2 routers in your network. They connect over 2 separate circuits to 2 separate routers on your upstream ISP. And this is the one that we're going to spend most of the presentation trying to figure out. As I say at the bottom there's no magic solution. It's like if I had $1 for every ISP who's asked me, just for the knob that lets them set this up and it all works perfectly. Unfortunately not with this BGP. Now, private autonomous system, that's being used more and more, which is good to see. You can use it, for example, if you have lots of customers who multi-home onto your network. So it's described in RFC 2270. It's quite a good description there. Or it can be used in a corporate network with several regions and connections to the internet only in the core. Obviously, it's used in confederations as well. But that's generally where private ASs are used. This is a really important thing which so many people still forget to do. When you're setting up an external BGP session, it's really, really good to make that default command. There's still so many instances of where private ASs are leaked to the internet routing table. It's not a problem in the sense that announcing RFC 1918 address space to the internet is, but still it's a bit, private autonomous system is not really meant to be appearing on the internet. And there are various rules about when you can use remove private AS and what it will actually do. But if you've got a customer using a private AS for them to multi-home onto your backbone, remove private AS on all your eBGP peering, the router will strip the private AS from the announcement. You'll see an example of that in the next few slides. Right, so now we're going to connect to the same ISP. We're going to use BGP for this type of multi-homing. We're going to use a private AS number. I mean, you won't get a public AS number if you go to the registries. At least you certainly won't get one from APNIC. And what happens is the upstream ISP will proxy aggregate. It doesn't really proxy aggregate anymore. The upstream ISP will announce your network to the internet just as though you were a statically connected customer. Okay? Now, as I say, there are lots of examples. So here's one scenario. We've got 2 links to the same ISP. We're going to use this private AS here, 65534. We're going to make the path between router A and router C the primary path, between router B and router D the backup path. Reasonably common situation. Some people have a primary circuit, say 2 megabits big. They have the backup one, 64K, 128K, just all depending. So they want to try and figure out the configuration to do this. And I wrote the slides. You announce your aggregate on each link. The primary link makes Okay, I thought this would die. The primary link makes the standard announcement. The backup link increases the metric on outbound and reduces local preference on inbound. And you're all aware of what metrics and local preferences do, I hope. So on the backup link, if you send a higher metric on the outbound path, your upstream will see it as a higher metric. Lowest metric wins. So basically, this path will be preferred over this one for inbound. So that makes it the backup. Likewise, for outbound traffic, you set local preference on the inbound announcement. If you set the local preference lower than the default of 100, that becomes the backup path. Highest local preference wins. Remember that. Right. When one link fails, we're announcing the 19 aggregate on another link, and life carries on as normal. And the configuration is this. And this is it. This is all you need. Right? You declare your autonomous system number. You've got your /19 aggregate. Your remote AS. You just use the Cisco AS. Then prefix list. We're going to send our aggregate outbound. The aggregate prefix list is defined here as that /19. From an upstream ISP, notice we're just going to use the default. Right? This, again, harks back from my days at Unet. For multi-homing customers, we sent them the default route. If they wanted the full routing table, well, we would sell them a bigger router and charge them lots of money for it. But generally, we just try to give customers the default because that's basically all you need. If you tell the customer you've got a default, if you tell the customer or give the customer a default route, you're saying to the customer, I know how to get to the whole internet. Okay? So they don't need more than this. So that's the router A configuration. Router B, well, this is the other one in AS65534. This is the one that hosts the backup path. Again, we send our aggregate outbound, and we accept the default inbound. But we're now using a route map to apply policy. Remember at the start I said prefix list to filter prefixes, route maps to apply policy. So in here we've got a route map. We're just going to apply our policy. This is the outbound policy. That is the inbound policy. If you remember from the previous slide, outbound we're going to set a higher metric. Inbound we're going to set a lower local preference. So the next slide does that. Outbound, we're going to set the higher metric, okay, assuming metric of 0 is the default metric. So we match on the aggregate, on the outbound announcement. And that's all we're going to send anyway to the upstream. But for the interest of doing it right, we're going to match on what we're going to send, set metric 10, makes it less preferred than announcement from router A. And for inbound, we basically set local preference 90 on everything, assuming the default local preference is 100. Okay, so that's router A and router B. Router C, this is in the upstream, in AS109. While he's peering with 65534, the default originate command basically assigns a default route. Okay, it assigns a default route originated from this AS to this peer. Prefix list, customer in, so we're going to accept only the /19 from the customer. And outbound, we're only going to send the default. This stage, people sometimes stop me and say, well, why do we need the filters here if the customer's got the filters on his side? Right? And this is such a common thing. It's like, well, would you trust your customers? Or you say the same thing to the customer. Would you trust your upstream? Right? I mean, if the upstream didn't have these filters, then the customer could send anything. They could make a mistake in the configuration, right? And suddenly the full routing table appears, or garbage starts appearing, and so forth. Put the filters on both ends. And one thing that I've always been taught, and people have always taught me, is you need two of everything in the internet. The multi-homing here, I'm saying, use two routers. Don't just multi-home with one. Right? People are doing multi-homing because they want more than one connection to the internet, for business reasons, commercial reasons, whatever. So it's worth putting filters on your customer side as well on your side. If the customer doesn't know what they're doing, then at least you're safe. Okay? And if we look at router D, this is the backup link, exactly the same. Right? There's no difference there at all. Okay, just IP addresses on the neighbor. See that?
Command switch the private AS.
Okay, this is coming on router E, right there. Okay, this is router E, this is the border router for AS109, and we've got the remove private AS here. So basically the announcement 221.10/19 has an AS path of 64534 only. That is stripped out, and all that the neighbors see it as is 221.10/19 originated from AS109. Okay? I mean, nobody else on the internet cares whether it's a private AS, whether it's a dual home connection onto this ISP. We don't care, right? The internet does not need that information. So this works just fine. And this is all you really need to do. But obviously, as you add more and more customers, you need to extend the prefix list to allow all the customer blocks. And that's the other thing. Right. Two links to the same ISP. So the situation where you've got one big circuit and then a little one to back it up, I mean, it's not too common. People want to try and load share between the two circuits that they've got, right? They tend to be international connections or expensive long-distance connections, so you want to get the most bandwidth for your money. So we're going to use the same idea as before, private AS, the two links, router E will strip for the private AS. So the best way to do it, keep announcing your aggregate, very important, and then split the 19 and announce it as two 20s, one on each link. And this is not the ultimate solution, but it's a place to start from. I mean, some people, I don't know, I find it amazing. They get the 19, and then they split it into 32/24s, or 32 class Cs, as they happily tell me, and they try and announce that to their upstream. And that's like, well, you know, why start with something complicated? Take a 19, split into half, see what you get. Do it in bite sizes. Right? I mean, this is a simple split. It assumes equal circuit capacity and an even spread of traffic across the address block, which you never, ever get on the internet. But it's a good place to start. And then you just simply vary the split until you get perfect load sharing, whatever perfect means. I mean, if you configure something for one day, next day it's going to be different. But you can start, say, 2/20s. If that doesn't work, well, try 1/20 and split the two 20s into two 21s. Right? So you announce a 20 and a 21 on one link and a 21 on another, and so forth. Start splitting it like that, rather than just chopping it all into 24s and seeing how you go. Also, from upstream, just take the default from them. Gives you basic outbound load sharing. For most ISPs on the edge of the internet, you care about how traffic comes into your network. It doesn't really matter how it goes out, because the traffic ratio tends to be about 70/30, 80/20. Okay? Right, 70% of it comes in, 30% of it goes out. So trying to do capacity management outbound usually isn't an issue. Okay? So router A configuration, this is in the private AS. So we've got our 19 there. We've got our /20, so it's the first /20 out of the 19 block. Prefix list, router C out. So in the router C out prefix list, we're going to allow a 19 and a 20. Okay, that's it. So you just announce the 19 and the 20 and set up the filter appropriately. Router B configuration, which I don't have, it's exactly the same as this, but we just use our second /20 here. So it'll be 221.10.16.0. And you have 221.10.16.0 there instead. All right. Router C, which is the upstream. Default originate, as we had before. You just send the default route to the customer. Prefix list customer in. Well, notice what I've done here. I haven't tried to figure out what the customer is going to send me. I've just said, oh, well, if he sends me 19s or /20s from that block, fair enough. Some people go further and do 19 LE 21 or 22. And that gives the customer more scope to fiddle with the load sharing rather than you having to be involved all the time. And one thing I always found is give your customers enough rope. You know, they like playing with the rope, especially if they get to fiddle with the BGP connection that they have to you. It's a good way for them to learn as well. Right. So here I put the load sharing configuration on the customer router. Some ISPs choose to put it on their router, so they'll send metrics to their customer and apply local preference to what the customer sends them. But I don't know, I don't find that very common anymore. Certainly when we're starting in the early 90s, your customers are like, ooh, internet, and they tend to leave the ISP to do things. But nowadays, it's more like, the customers learn a little bit about BGP, is quite happy to have access to the routers and actually start playing with some of the load sharing. So example here, all the configuration is on the customer router. Upstream ISP's got very little to do, in fact. You only have to remove the customer sub-prefixes from external announcements. His customer's got a 19 block, so make sure you announce the 19. There's no point on earth for announcing any sub-prefixes from this 19. Okay, absolutely no point whatsoever. And remove private AS from the external announcement. Then again, as I said before, all eBGP configuration, please put the remove private AS command on there. If you want it on by default, speak to your favorite vendor or vendors. Right, RFC 2270. This one's quite interesting. I think this is quite neat. We certainly implemented this at UUNet in the UK way back. And it just makes a nice, simple, scalable way of having lots and lots of customers multi-home onto your backbone. UK internet starting up, there were a few ISPs in the beginning. We tend to find that our customers wanted to multi-home onto our backbone rather than between two providers. So to have a nice, scalable way of doing this, well, the RFC actually came along at the convenient time. Use a private AS, and yes, you can use the same private AS number for all of this. So let's have a look at how all this works. You can use the same private AS. We don't have overlapping address space, obviously not. Customer is only going to hear a default route, so you don't get any AS path loop problems. So it's quite easy to do this. And the router A and B configuration is the same as the A and B configuration we've had before. If you're using templates to build your customer configurations, this makes life easy for you. You don't have to build custom configurations for multi-homing customers, right? I abhor networks where you have to build custom configurations for every service you sell. If you can make a configuration fit for one service, for every customer you get, it just makes it much easier to train all your support staff, your network operations center, and your engineers. So, router A, well, say A1. We've got the 19 and the 20. Remember, we're taking the 19, splitting it into two 20s. We always announce the aggregate. So, prefix list, router C out, so we send this to our upstream, we accept the default from our upstream, and the static routes to put the entries in the routing table. B1 is the same configuration. Router C is where it gets interesting. This is where you get the sort of economy of scale for configuration. You can set up a peer group, right? They're all the same. If you don't know a peer group, it's a way of bundling configurations that have the same outbound policy to make it more efficient for the router to make your BGP scale better. So in this peer group, while we're all in remote AS 65534, we're going to do a default originate to everybody and prefix list default out. We're only going to announce the default route outbound. And then we just apply the peer group to all our customers. So for this first one, customer 1, peer group, BGP customers. We still have the individual inbound prefix list. Each customer will have their own address space, so we just have prefix list customer 1 in, customer 2, customer 3, 4, 5, and so forth. Right, so this makes a very simple configuration on your backbone routers where you aggregate the connections. Okay? So here we've got all the customer prefixes. Different ISPs do it in different ways. I've seen one who just has one whopping big prefix list used for all his customers, and he just keeps adding the customer networks there. And the downside of that one is, well, one of your customers announces address space that belongs to another customer, you might have an issue, but it's really up to you how you want to try and run this. But this works just fine. Router D configuration is identical. Now, if we look in router E, well, here we assume the customer address space is not part of the upstream address block. So the customer will have got address space from regional registry, say. So I'm assuming, say, neighbor, remote AS110, we've got the remove private AS command, and then neighbor, prefix list, customers out. Then we list a prefix list with all our customer address blocks in there. Okay. Now, again, as before, within AS109, the private AS is visible. It just looks as though you're peering with AS65534, and 65534 has lots and lots of address space. Right? So that's RFC 2270. That thing's actually really good. Rather than having proliferation of multi-homing between all sorts of providers, if ISPs can actually offer this as a service. I mean, it's not hard to offer, and the configuration is actually quite neat as well. Diversity onto the same backbone is probably a lot more efficient than providing diversity between different service providers. If the customer's prefixes come from the ISP address block, don't announce them to the internet. Some people do this. Right? They give address space to a customer, a huge chunk, and then they announce this huge chunk to the internet, even though it's part of their aggregate. Only announce the aggregate. There's so much pollution in the routing table. My view has got 110,000 prefixes. That's the view in Japan, and it was 106,000 for about last 6 months or so, and it suddenly just rocketed off. And I can't really see any reason why. It just seems to be a general increase again. Okay, so try and be efficient what you announce. Announce the aggregate. Don't announce customer sub-prefixes if they come from your block. And it's quite easy to do. I mean, this is another excuse. People say, oh, it's too hard. What's too hard about a one-line filter like that? That basically blocks all the sub-prefixes, only allows your aggregate outbound. Right, connecting to different ISPs. For this one, you need to use a public AS number. You don't have to. I mean, you can use a private AS if you can agree with the other ISPs. I mean, I know there's some ISPs out there who've agreed to use a private AS number for all their customers who multi-home between them. So, I mean, if you can do that, well, that will work as well. Okay? Address space, well, it can come from both upstreams or it can come from the regional registry. Concepts are actually quite similar. So let's have a look at, we'll go through these again. So this one's the primary link and the backup link. Again, always announce the 19 aggregate. Keep announcing the 19 aggregate. The primary link is just going to make a standard announcement. The backup link, well, we're going to use AS path prepend for this. Okay? We can't use metrics because it's going to different ISPs. So we use AS path prepend. Okay. And again, when one link fails, because we're announcing the 19 on both links, we have continued connectivity if any link fails. Right, the picture looks something like this. We've got 107. This is going to be the primary path to the internet. That is going to be the backup path to the internet. On this link, we simply announce the 19 block with a longer AS path. That's all we need to do to make it the backup. Right. I'm going to configure this so that E to D or 107 to 108 is just the backup link. Okay? So the primary traffic path will be coming in through this way. Some ISPs do this. And this could be, well, thinking back home, this could be an expensive transit provider who charges lots and lots of money per megabyte, and this one does it fairly cheap. So you want to try and attract all your traffic this way and only use them for dire emergencies.
How do you control the inbound?
Yes, path prepend. So I'm just about to put up. So this is router A. This is the primary path. Okay, so we've got our /19 here. We announce it outbound. We accept the default only. Notice I'm only accepting the default from upstream. The second half of the presentation will cover situations where you don't want to accept the default. But for this case, we're only using the default because remember, as I said, most of the traffic, it's more traffic coming from the internet than is being sent to the internet in most cases. Okay, so that's router A. That's simple. This is going to be your primary path. Router B configuration. Well, this is the backup. This is going to AS107. sorry, 107 to 108. We send our aggregate outbound. We accept default in only. We're going to use the route map, router D out, route map, router D in to apply our policy. Now, route map, router D out is going to be used for the AS path prepend. And it's quite simple. Route map, list, that's name, permit. For everything, we're simply going to set the prepend to 3 AS107s. Okay? Some people put in 20 ASs there. It's like, why? That's never necessary. The way to figure this out is go to a looking glass in the center of the internet, wherever that is. Okay? Go to a looking glass and figure out the paths and put in enough prepends. Then, working on the vendor side of the fence, the number of requests that we've had for limiting the AS path length or the prepend announcements that can be received. That's obviously causing a lot of people a lot of problems these days. So, maximum AS path. There. So be sensible with this. Some people just to make absolutely sure it's back up, they're going to put in 10, 20, 30, whatever. There's no need for that. Look at your upstream, look at your path to get to the center of the internet, wherever that is, and figure out how many you need to put in there. Make sure it's your own AS number. Right? This is like second stupid mistake people make. Don't use somebody else's AS number. I mean, yes, you can do some really neat tricks and so on by using other people's ASs, but use your own AS number. Now, for inbound policy, well, to make this the backup link, we're going to lower the local preference. So everything that we're going to hear from router D, we set local preference 80. This is lower than the default local preference of 100, which router A hears, so this is going to be the backup path for outbound traffic. And this works. This works just perfectly. Yeah?
If the customer has another router within their network, and only one link that goes to router C,
okay.
traffic bound for the internet will hit B and will take the backup link going out, or will it go to router A?
Well, well, you need to run the full IBGP mesh, for example, and so your router, wherever it is, will pick the best path based on what IBGP says. So this router, whatever you want to call it, will see a local preference 80 from router B, local preference 100 from A, so best path is through A. Yeah. Router B is going to see IBGP session with router A with a higher local preference than it's got itself. So it's going to best path stuff out towards router A as well. Okay. So, right. Load sharing. This is a simple cut of load sharing. We're down to 19 on each link. 19 split into two 20s, one on each link. This is fairly basic. Notice I'm still announcing the aggregate. Remember the net police filters I mentioned before. You want to try and load share between yourself and your upstreams. You don't care what 20 ASs away in Internet C. So don't send them the garbage that you're going to announce just to get your local load sharing right. Okay, so split the 19, announce it as two 20s, but make sure you announce the 19. Okay, the aggregate. This is basic inbound load sharing. I mean, nobody really does this because this is such an idealized situation, but it's a place you want to start from. That's the important part. Okay, so the picture is like this. 107, router A announces the 19 and the first 20, router B announces the 19 and the second 20. Right, so you're announcing 19 out of both paths, and then the first 20 one way, the second 20 the other way. So all the traffic for the first 20 will come in this way, the traffic for the second 20 will come in that way. Okay? And that's quite simple. Even traffic from AS108 to get to the first 20 will come around that way. Right? Remember, longest match lookup and IP. People forget that. They seem to think that, oh, well, if I do an AS path prepend or if I send a metric, somehow that's going to override the longest match lookup in V4. Not the case. Okay, so the first 20 will go around this way, the second 20 will come in that way. So you get pretty good load sharing just to start with if you've got evenly space use of traffic over your address block. Whenever I'm setting up configuration for ISPs or trying to show them how to do it, I start from this. Right? Rather than trying to get a horribly convoluted configuration, I start with something like this and work from there. Configuration to do it, well, it's the usual stuff, the 19, the 20. We're going to send the first block out, accept the default in. Right? We've seen it before. B, same thing. The 19, the second 20, second block out, down here. And again, we're only going to accept the default from the upstream. Okay? It is quite simple, so I'm not going to spend too much time with configuration. More controlled load sharing. Well, I don't know about control, but this is like another way of trying to change things. Again, we're announcing the 19 aggregate on each link. Really important. The first link, we just announced the 19. On the second link, we announced the 19 with a long AS path and announced 1/20 sub-prefix. Right, so again, that can control load sharing between upstreams and the internet. And we just vary the sub-prefix size and the AS path length until we get perfect load sharing achieved. Right? This is really another way of doing it, and it's giving you hints about how you try and figure out how to balance the traffic coming into your network. The picture is this. We announce the 19 by default out here. Out this way, we announce the 19 with a long AS path, and we announce the 20 sub-prefix. Right? Wonderful. So traffic for the 20 sub-prefix will all come in this way, and traffic for everything else will come in that way. The reason I do the long AS path is so that this 19 is preferred over that 19. Okay? That's another way of doing it. And this time, we want to announce one sub-prefix to the internet routing table rather than two in the previous example. Configuration, well, route array, very easy. We just announce the aggregate, just accept the default from the upstream. Router B needs a little bit more work. We've got the 19 here, we've got the second/20. We accept the default from our upstream, and we send the sub-blocks out to our upstream. And the sub-blocks we're going to send are basically, well, /19s and /20s. Now, I've only put a 19 and this 20 into the routing table, so this prefix list works just fine for me. And then the route map to set my policy outbound. The policy I'm going to set is do an AS path prepend. So in this case, I've decided to do a 2 times prepend. Again, you need to play with this variable to find out what actually works. But I find in a lot of situations with the picture that I've shown you, this works. It gives you pretty good load balancing for a lot of the smaller ISP networks that I've touched. Okay? And it's very, very efficient on the internet routing table. Now, this is probably the second half. This is the more interesting part, the more challenging part for people to try and figure out. So I've called it service provider multi-homing. And what this is trying to concentrate on is traffic flow out of your network as well as into your network. So, right, as I said, the previous examples dealt with load sharing inbound traffic. What we're now going to try and do is figure out how to handle outbound traffic. ISPs who are not on the edge of the internet, they've got maybe ISP customers of their own, they're seeing pretty much equal traffic flow to their upstreams or to their peers. Multi-homing is a bit more of a challenge for them. In fact, a lot of transit ISPs are working quite hard to balance traffic flows in both directions, to balance link utilization and actually try and keep traffic flows symmetric. There's quite a bit of effort being made, certainly in Asia, to try and do that. Because asymmetric flows across the Pacific Ocean to land here in the States is, painful. Certainly if you try to get from Australia to Japan, then it has to go across the Pacific about 3 times. It just varies. It depends how you connect and so forth. The question was, what was the success rate? It varies. It depends where you are and who you're connecting to and so forth. It's generally very difficult. But rather than people saying, throwing their hands up in the air and taking all the address space and announcing it as Class Cs, I'm trying to get people to be a little bit more efficient about what they're trying to do. Now, balancing outbound traffic requires inbound routing information. So the common solution is, oh, well, sir, you need the full routing table. Right? I've come across so many situations where it's like, you need the full routing table. Why is the full routing table just such a big thing? Why is it so fashionable? I mean, for the router vendors, yes, it is, because they get to sell you lots and lots of expensive equipment with lots and lots of expensive memory. When in fact, you can do a lot of this stuff with bog standard, off-the-shelf, cheap routers. Okay? It's rarely necessary. You know, it's Jeff Houston's routing mallet. Why try and use all these huge routing table, 110,000 prefixes, simply to solve load sharing between two networks that's immediately connected to you? I mean, it's really not worth it. Keep it simple. You really want to try to keep it simple. It's often easier to do it, costs a fortune less, certainly much cheaper than carrying n copies of the routing table. So I've got lots of examples here. These are typical ones I see around the world. One upstream, one local peer, an upstream and a local exchange point. Two upstreams, one local peer, tier one, regional upstreams, local peers. That one's quite complex. Disconnected backbone, which I threw in for amusement, because people just say, oh, you can't do that, but you can. IDC multi-homing, so Internet Data Center multi-homing, just an idea. But all these examples use BGP, and you need a public AS number for them. So, first one. Well, this bullet is going to appear in every single example. Always announce your aggregate. Accept the default route only from the upstream. You only need the default. Right? So, either use this one, I mean, there's no problem doing default originate, or just accept a network which can be used as default. Some ISPs have policies are not, about not announcing any default anywhere, even to a customer. So get them to send you a network which you can use as default. Okay? And for the local peer, we're just going to accept all routes from the local peer. And your local peer is going to have, what, a few hundred? That fits into a few hundred K memory in the router, so it's no big deal. Simple picture. Well, spare you that. Router A connects to the local peer. Router C connects to the upstream. Router A, we'll go to the local peer. Well, here's our aggregate, remote 108. We're going to send our block to the local peer, so just our aggregate out. And from our local peer, we're going to accept all the prefixes. So I've just made up some numbers. Okay, so those are two address blocks that our local peer is going to send to us. Okay, so that's quite easy. You can use prefix lists. I mean, some people just use an AS path filter list, which I think I've got an example of a bit later on. Yeah, here it is. Some people use the AS path filter. Okay, well, you basically say, well, I'm going to accept everything that my local peer is going to send me. Everything here originates from AS108. This funny nomenclature is basically there to allow your local peer to do AS path prepend. This says accept any number of 108 in sequence. Okay, so if your peer does a prepend of 108, it will get past this filter as well, which is what you want. Okay, so that's alternative configuration for router A. To be honest, most people take the two configurations I showed you and put them together. They have the prefix list to filter the prefixes, and then they have the AS filter to filter the ASs. The idea being is if the prefix list gets blown away, the AS path filter is still there, and vice versa. Remember the two of everything. Router C, similar thing, got a /19, remote AS107 to our upstream. We accept just the default, and we send just the /19. Okay? And that's pretty much all you need to do. Now, as I was saying before, two configurations are possible for router A, but some ISPs use both, just for safety. If you look at a lot of the presentations or current wisdom, having more than one set of configuration to do the same thing is a good thing. And amazingly enough, local traffic goes to and from the local peer. Everything else goes upstream. But again, the amount of situations where I find the upstream says, oh, if you're peering to somebody locally, you need the full routing table. It's like, well, why? What for? Okay? You don't. Right. One upstream local exchange point. This is very similar, actually. You announce the 19 aggregate to every neighboring AS, accept only the default route from the upstream, accept all routes from the exchange point. I'm assuming this is a reasonably small in-country or in-region, in-state exchange, not an exchange that's carrying about half of the internet routing table. Okay? So most exchange points, maybe 1,000, 2,000 prefixes typically. So a pretty picture would look like this. Router A connects to the exchange, router C goes to upstream. Router A configuration, well, that's made up of Ethernet connection, so fast Ethernet connection onto the exchange point LAN. And then the BGP configuration, well, we've got /19. We've set up a peer group for the exchange point peers. Again, all the peers are going to have the same outbound policy, so we stick them in a peer group. I've used soft reconfiguration. There's probably no need for that anymore. Route refresh is out there as a standard. And then, the prefix list, my block out. So my block is your /19 or whatever you're going to announce to your peers. And then you just apply it to all the exchange point peers. Right? So remote AS100 gets that, 101 gets that, 102 gets it, and so forth. You still filter your exchange point peers inbound. If you know what they're going to announce to the internet or to you, make sure you put them in a prefix list. Still amazing the amount of people who accept anything from the eBGP neighbors. You could do that in 1994, 95. 2001, nah, you need to filter everything. What this does is let you reset the BGP configuration or change policy in the BGP configuration without having to do a hard reset. Okay? Previously, the old way of resetting policy on a BGP peering was to put the peering down and bring it back up again. You don't want to do that on the internet today, because it means your prefix vanishes from the internet. Route flap damping is used by most ISPs. You're only going to slap it once, but I've seen even one flap ending up being suppressed. Some people run really aggressive damping parameters. Ideally, I'd like people to use the right 210 values. They're less aggressive than even the Cisco defaults. But some people are damping even one flap. So, yeah.
One advantage of that is with that,
That's right. Yeah.
And the second thing is, when you do it, you have enough RAM.
Yeah. Again, I put this example up because it's exchange point. It's a few prefixes. Doing a soft reconfiguration on 110,000 prefixes is eat memory time. That's why I generally don't recommend this unless you come across a neighbor who can support route refresh, or you want to find out what you're getting from your neighbor before you apply your policy. Okay. Route refresh is automatically negotiated between routers anyway. So, that's probably, I'll just put that in as an example. It's basically because at the NSPI-XP2 exchange point in Japan, about half the peers there still don't support route refresh. And I've lifted that configuration quite literally from a router I've got access to. Okay. All these configurations, by the way, are working configurations. They're not cooked up. I've just changed the IP addresses and some of the policy to protect the innocent, but these are all real. Okay, so that's the peer group used for the exchange point peers. And then, you just have the prefix lists that you apply for the BGP peering from each neighbor. Okay, so it's actually quite simple to do. Router C, which connects to the upstream, well, this is the same as it was before. We accept just the default. You only need the default. Default says, I know how to get to the whole internet. You don't need to send 110,000 prefixes to your customer just to tell them or prove to them that you can get to the whole internet. I suppose it's a bit like a status thing. Some people always want to buy the biggest and the best just to show that they can do it. But default is all that's really needed to do. Okay. So note the router A configuration. Prefix list is higher maintenance but safer. I didn't mention the unicast reverse path forwarding. If you went to Barry and so on session this afternoon, and that's actually a really, really important thing to have on, certainly on all interfaces on the edge of the internet. You're not doing funny load sharing here, so unicast RPF can just be stuck onto the interface without really worrying. Okay? We're using unicast RPF for the network here and at NANOG itself, so generally should be gone on the edge everywhere. And again, you find exchange point traffic goes back and forth to the exchange. Everything else goes to the upstream. Let's carry on. Right, so this is just another example. I'm skating through these quite quickly because the slides are actually on the website, and there are lots of configuration examples, which actually are quite repetitive, but you can go away and study these in your own time. I want to just really get over the salient points and some of the concepts. Again, announcing the 19 aggregate in each link. Really important to do that. Again, we're accepting default route from the upstreams. So it's either network 0 or a network which can be used as a default. And from the local peer, we just accept all prefixes they're going to send. Pretty picture looks like this. 109 is the local AS. You've got your local peer in 108, and your two upstreams, 107 and 106. This is the simple one. So A configuration is exactly the same. It's simple router, simple peering. Got the configuration in the slides before. Router C, this is going to the first upstream. Got the /19. Again, we're only accepting the default, right? Then again, if you're connecting to two upstreams, the standard thing I see is, you need 2 copies of the full routing table. That will be a Cisco 7200 you'll need. And then the poor ISP goes, whoa. Okay, they don't need it. Whereas you can get away with this simply by doing default as a first cut. That's a prefix list default in, and you just announce your aggregate out. Okay. Router D, what changed between these two slides? Very little. Right, just the address and the ASN. Okay, again, you accept just the default from the upstream, and you basically will get nearest exit. Traffic will go nearest exit to whichever router is closest to get to your actual upstream. And the amazing thing is, you don't need expensive routers to do that. I mean, there are no salespeople here, so I can say that. It's not useful in practice, especially for international links, which I'll show you in the next example, because it's a fairly raw first cut at load sharing. I mean, nearest exit is not wonderful. You end up with some asymmetric routing. In the case study I'm going to show you right at the end, I mean, you just couldn't do it this way, because there actually was load sharing between Europe and Asia, which is very extreme distance apart. So, better configuration options. Or you can accept full routing from both upstreams if you really want to. If you've got the memory and the router, do it. And you can show everybody who comes into your equipment room, oh, look, I've got 2 copies of the full routing table and so forth. Yeah? Yes, I mean, from a Cisco point of view, anything which runs iOS and supports BGP, that's the minimum configuration. So I've seen this being set up on, well, 1000 series. Little sort of plastic thing. 2500s, this works fine. A lot of African ISPs do this. 2500s, that's all they usually run. So, actually, the best way, most efficient way, is to accept a default from one upstream and some routes from the other upstream. Right? That's actually the nicest way to do it. Because there you're only working with, well, today probably 15, 20,000 prefixes. That fits quite happily into 32 megabytes of memory, typically. And that's really the way to go. I mean, you don't have to work hard to make this function. But as I'll show you towards the end, I mean, the resistance I met from the two upstream ISPs concerned to do this, it's quite amazing. You're just virtually refusing to talk. But anyway, if you want to do full routes, well, remote AS107 is the upstream. Prefix list RFC 1918, that's basically Bill Manning's list. The special use addresses block all those, except everything else in. Outbound, you only send your /19 block as before. Route map, AS107 load share, well, whatever that is. I mean, you need to do some kind of load sharing. You've got two full feeds, so that's just some route map. For example, everything that's originated by our upstream and upstream's neighbors, immediate BGP neighbors, we're going to set a high local preference on. Okay, so traffic to all these guys, 107 and the AS neighbors, we're going to send out this way. Everything else we're going to set to a low local preference. That's just one example of what you can do. There's so many variations on this particular theme. Pardon me. And for router D, we just take everything. Again, we set up this prefix list, which is Bill Manning's draft, as I said. Accept everything, 110,000 prefixes. Outbound, we send a /19. Okay, and this one will work. And this is quite a common one, which is used a lot. Unfortunately, it needs huge amount of memory. And again, having chew through 110,000 prefixes, work out best paths for all these. It does take CPU time and load on the router to actually make anything function. Yes. That's why I was a bit dismissive. Yeah. Why am I modifying the local preference in the previous slide? I'll just put the previous slide up. Why am I modifying the local preference? It's simply an example. Yes. Yeah. For this particular one. I mean, yes, the standard AS path selection process will figure out the best way, but maybe this isn't quite enough, and you need to do a little bit more massaging, for example. So I could do something like this, and generally to try and get traffic staying roughly symmetric. I don't want AS107 traffic to go to whatever the other AS was, 106 or something. So I want to try and keep it reasonably symmetric as well. So that's the only real reason. It doesn't have to be like this, but I see this one used quite a bit. Okay, that one is simple. So router C, accept full routes. Tag prefix originated by 107. Blah, 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 blah. Yeah, okay, we've discussed that, so I'll just move on. Right, full routes from upstreams needs 128 megabytes of RAM. You need to play preference games because not often does the AS path actually suffice. As I said, it's only an example. You need to do lots of fine-tuning in real life. And the thing is, you can't provide a scenario that will work for every multi-homing situation. It depends who your upstreams are, what connectivity they have, and so forth. Okay? I think I'm really putting it up to try and put people off going down the full routing table path. This one is using partial routes, where you accept the default route from one and a few prefixes from another. This one is light in memory, light in the CPU power that it needs, and it's configured like this. Prefix list, well, we're going to block RFC 1918 prefixes, and we're going to allow the default route in. So we're basically going to get our upstream to send us a default as well as the full routing table. Prefix list might block out as before, but the filter list and the route map are the key to applying the policy. Yes, our upstream is going to send us the full routing table, but we're going to filter it. We're going to filter it using the filter list and the route map. And the filter list is basically this one. We're going to allow everything originated from 107 and from 107's neighboring ASs. Okay? So that will give us, well, I don't know, it depends who the upstream is, but it can be anything, 5, 10, 50,000 prefixes, whatever. And then the route map, well, tag default low is basically going to set the default route, which the upstream will send us. We'll just set the local preference low. Just an example. Again, I'm assuming we're taking a full IBGP mesh across our backbone. So we set local preference low on the default, so the default route that we hear from the other upstream will take priority. Okay? And the router deconfiguration is very easy. We just get the default. Just get the default from the upstream. To our upstream, we just send our /19 as before. And this is a light way of doing multi-homing. And the amazing thing is, you configure this and compare it with the previous example, you get exactly the same effect. Right? Exactly the same effect, but you're doing it with probably, well, 200,000 prefixes fewer. Okay? Right, 200,000 paths fewer. And that's a lot of saving in the memory and so forth that you need in the router. Another thing is that it's not only memory you've got to consider. You've got to consider BGP convergence time. If a path changes, how long is it going to take for the router to figure things out? If the BGP session resets, well, 110,000 prefixes, depends on the circuit capacity, the CPU load. You have to take 2 minutes, 5 minutes to actually get all that onto your router. With the default route, it's there, just like that. Okay, I've said all that. So yeah, partial routes, not expensive. Need to filter an AS paths, but that's all right, no problem. Again, it's only an example. Real life will need a bit of fine-tuning. The example I'll show you at the end has all those. Right. When upstreams won't announce the default route, just use prefix that you can, well, just use something that they'll send you as a default. Another thing to do is use IGP to propagate a default from the edge or the peering routers. Okay, that's the other thing that you can do. So it'll be something like this on router C. Default information originate. We set it up as a metric of 30. So that will be the backup path. And it's the same configuration as before. And then on the other router, we set up a metric of 10. So this will be the preferred default. Okay, for outbound traffic, if there's no better path learned from the BGP session on router C. Okay, so again, router C is going to take everything from the upstream, block the private addresses, the filter list 10 inbound is here. It's basically, you're going to allow prefixes from your upstream AS and from their neighboring ASs. Okay? And this is a very common way of trying to do it. And you point the static default route with a very long distance to the upstream. Okay? The serial interface goes down, the static route is removed from the routing table, the OSPF originate disappears, and then the other path becomes the default, and vice versa. Okay, so let's jump over this. Yeah, so there's the other static route default pointing to the serial interface, just as the backup. Right. Now this is the fairly complex one. Actually, it's quite a common Asian one where ISPs will connect to each other within the region. They go to Singapore, they'll connect to Malaysia or to Hong Kong or somewhere, or Japan. And then they'll connect directly to the US. To configure this, well, again, we set the 19 aggregates on each link. Make sure we announce these. Try and accept partial or default routes from the upstream. Again, taking 4 copies of the full routing table is a bit extreme. Some people do this quite seriously. They take 4 copies. Because the regional peers, well, they take the full table from them as backup in case their own links to the US go down. So Carrying four full routing tables is quite common. But there's no need to do it. You can do it quite easily with just partial and using default routes from upstream. Okay? The way we're going to do it is accept all routes from the local peer, because when they're just local, they're in country or across the border, a few prefixes. Accept partial routes from the regional upstreams. So the regional ones are going to be in your locality. So you can accept prefixes from them and their immediate neighbors quite possibly. And then the tier 1 upstreams, well, you just need to get a default from them. You don't need the full routing table really. So picture could be something like this. Right, local peers, regional upstreams, regionals, local exchange point. This is quite common. Now, router A, it's a local private peer. We accept all local routes as before. It's the same type of configuration. Same with exchange point. Just accept all the prefixes you get from the exchange point. People don't offer transit across exchange points, or they generally don't. They generally shouldn't. So you don't get a large number of prefixes there. So carrying all those in your router is usually no problem. Now, regional upstream, this is slightly different. They provide transit to the internet, but they have a longer AS path than to the tier 1. Obviously, you're going to connect to the tier 1 as your primary path. But if that fiber across the Pacific or wherever it's going gets cut, you want some type of backup arrangement. So the way to do it is through a regional upstream or regional peer, whatever you want to call them. But they'll offer better paths to themselves and their immediate neighbors than going directly to your tier 1. Right, so you can accept prefixes from them and the neighbors. Right, so you may need to massage this. This is just a general example. Ask them to send you default, or send a network you can use as a default. Set local preference on this to 60, for example. Set a very low local preference on this default. So it will only be used as a backup when everything else is gone. Okay? Router E, which connects with other regional upstream, same thing. AS111, we accept his prefixes and his neighbor's prefixes. Okay, again, ask them to send a default or a network which can be used as a default, and we set local preference to 70, for example. I'm just structuring my local preferences. So this will be my third backup. The previous one was my fourth backup. Was my fourth possible backup path. Okay, and then we'll go to the tier 1. This is the first tier 1. Accept all the customer and AS neighboring routes from them. Again, to try and get reasonable symmetric routing. Accept all their prefixes they originate and the prefixes their neighbors send. Okay, ask them to send a default. Network you can use, blah, blah, blah. Default, we set local preference to 80. So this becomes my second backup. Okay, and then the other one, router D. This is the one that I can use as my primary path to the internet. Ask them to send the default again. We leave the local preference alone. Okay, so this is going to be the primary path. All traffic is going to go here unless there's a more specific path. Okay, so this is actually a very complex multi-homing situation set up, but I've done this one with one ISP, and they're carrying about 20,000 prefixes, and it's, rather than carrying 4 full feeds that they had before, they're now carrying 20,000 prefixes, and this works better for them, they reckon, than trying to do it the way we did it before. Yeah. Yes, I mean, this is basically saying that there can be caveats with trying to set this up with the different local preferences and so on. I mean, I think I've roughly got the gist of what you're trying to say. I mean, yes, there are. I mean, this is an example of where to start from. Okay, that's how I like to see it. It will need massaging to get it exactly right. And if you find that this local traffic is going to your tier 1s because of this, then you have to make the alterations. What I'm trying to encourage is people to not panic and think they need the full routing table and start from there, working backwards. Whereas you start with this somewhere light and then make the necessary adjustments to make it work. I mean, I find this actually works a lot better. But yes, you're right. You've got to watch how you set your local preferences. Otherwise, things can get a bit funny. Oh, I see. Okay. Yes. I've missed the... Uh-huh.
And checking that back over your transit.
Yes. That's a downside. Yep. I agree. With just using a default. Yep. I mean, I think a lot of these things have to be weighed up. I mean, it may not be so much of an issue within the NANOG community, but certainly for a lot of the rest of the world of trying to do multi-homing without having to go down the path of massive routing tables and so forth, it's quite a key thing. Right. Mm-hmm.
How do you decide if you want to totally pick up the small subset of routers that way you have some control?
I mean, basically, if you don't want to carry 2 copies of the full routing table, you have some control by accepting default from both and then a small subset from one. Or accepting default from one, pointing a static default to the other, and accepting a small subset from the other. That type of scenario. Yeah. Right. Okay. I've talked through all that. Yeah, I'll jump through this. Yeah, and that. Right. Let's do this one. This disconnected backbone. Where ISP will run a large network, but the network has no backbone. ISP is basically in each city or whatever. It's got large point of presence in each location. Each point of presence will multi-home to upstreams. Quite common where we can't get backbone circuits. This one's quite interesting. It was a case basically where the service provider wanted lots and lots of AS numbers and the registry went eek. And you can actually do this quite happily with one autonomous system number. The pretty picture is like this. So all the different cities, there were a lot more than this in the particular case. And there were multi-homing between 2 upstreams. And people look at it and think, well, can you do this with one AS? Well, you can. The standard thing is, oh, well, it's loop detection. The AS loop detection will jump in here. But you don't need it. Each city will operate as a separate network. Again, you're relying on using a default route and leaking selected prefixes to get your load share. Okay. So router A, which is basically in the first city, was connecting to one upstream AS108 and another one AS110. We accept the default route from one upstream, and we accept basically the full routing table from the other upstream. This is the example I had before. Default from one, full routing table from the other. We filter out the private addresses as before, and then we apply a filter list to filter out what we want to try and balance the traffic load. Okay? So this is the filter list that's used for balancing the traffic load. So from the AS110 peering, we're going to accept prefixes from 110 and from their neighbors. Okay? And then we have a static route, default route pointing to the serial interface, and this is the this is the AS110 peering. In other words, the one that's sending us the routing table rather than the default. Okay, so you see how this works. Static default pointing to one AS, the AS that's sending us partial prefixes, and then we take the default from BGP from the other AS. So if AS108 vanishes, then this default will take over. If this interface goes down, this ISP vanishes, then the default other way takes over. We don't actually hear any prefixes from our other locations coming in here because we're relying on defaults for outbound traffic. Okay, that's basically what I said. 8108 peering, just receive the default route. We announce the /22 address. With 110, we receive the full routing table, filter with the AS path filter. I mean, if your upstream is nice to you, they'll probably apply the filters that you want so you don't get the full routing table over your link. But very often they tend not to do this, and you just apply your own filter to throw away the prefixes you don't need. Again, you announce your /22. We're going to take the 19, of course, and split it into pieces that will fit each location. Then we just point a backup static default in case the link to AS108 goes down. Okay, and that works quite nicely as well. Okay, there's no loop detection because we're relying on the default route. Right. Oh, by the way, important, don't announce the /19 aggregate. Okay, you can announce the 19 aggregate, but well, if one of your locations goes down completely, then traffic that's intended for it can vanish. You can end up with black holes and loops and so on. So there's not really any point announcing aggregate in this case. This is one of the situations I mentioned earlier where multi-homing gets hard in some parts of the world because of the registry boundary filters that are in place. Data center multi-homing. It's because I gave this presentation a few months ago, something like this one, and somebody from an IDC said, but. So yes, there's certainly problems here, and this is my first stab at actually trying to figure out how to do it for people with smaller address space. They don't have their own address blocks, it's actually harder to try and do this. It's also true for smaller ISPs and enterprise networks, whatever they are. Smaller address blocks are being announced. Address space comes from both upstreams. And actually, I mean, it's worth trying to apportion address space according to the size of the circuit to the upstream. I mean, if it's typical IDC, I suppose, the ones I've seen, tend to have about the same amount of traffic from each /32. Or at least they can proportion it out quite usefully like that. So apportioning size of address space to the size of circuit makes some sense. All right, so my picture could be something like this. We've got local peers, we've got our upstreams like that. This upstream has given them a /24, this one's given a /23. This circuit is 2 meg, this circuit is 4 meg, for example. So here I've picked the address space from upstream according to the size of circuits. Now, router A and B, these are the ones that go to the local peers. It shouldn't actually really matter what you do here. Just accept everything from the local peers, send everything to the local peers. It's a private connection to another provider close to you, so you can just basically send them everything you've got. Router C to the upstream, it's a bit different. We're going to accept partial routes from 107, as we did before, and ask for a default as well. And we set the local preference on the default to 80 to make it the backup. All right. Outbound, we send the 24 and send the 23 with an AS path prepend. Now, we got the 24 from AS107. The 23 with the AS path prepend means it becomes the backup path for that prefix. Again, I don't know what the reachability of this /23 will be. And the 24 obviously is part of the AS107's address block, so it will be announced as part of their block. But the 23 may only get so far through the internet, which is the downside. Router D, ask for a route to use as a default there. We leave the local preference at 100. So that becomes the default path, unless there's something more specific. Outbound, we send the 23, which we got from the upstream in any case, and we send the 24 with an AS path prepend. Now, in an ideal world, this will work just fine, because the 24 will be sent all around the internet, as will the 23. Okay. Now, for local fine-tuning, I didn't say this, but that's what I was told. it's actually quite easy to increase circuit capacity. Right? I mean, local circuit capacity could be across the city, across the street, across the block. For longer distance, well, then we've got to start playing with the AS path filters and the AS path prepend for what we accept and what we're doing with the prefixes that we receive from router C. Okay? So these are just some ideas. I mean, there's obviously a lot more can be talked about here that I haven't even thought about or looked at trying to do. Redundancy is quite important. Circuits should be terminated on separate routers. And apply a bit of thought to address space usage. I mean, I was even doing this way back, 3-4 years ago, 4 or 5 years ago, trying to figure out address space usage according to what we saw customers on the web servers we were hosting, what the traffic was like, right, to try and actually load balance a lot of it. I mean, some people just, get some address space, fill it up, get the next bit, fill it up, and so forth. But if you're careful about how you allocate address blocks according to, server busyness, then it can help with load sharing quite a bit. Failover, well, yes, that's what I mentioned before. 24 and 23 from upstream's blocks are announced in the Internet Routing Table all of the time. There's no obvious alternative at the moment. If you can have any good ideas, domain working group, multi-fix working group, would love to hear from you. And there's a conditional advertisement, which is certainly in Cisco iOS. It can help in the steady state, but again, in the failover, you need to announce these small prefixes to the routing table. And a lot of these prefixes will be filtered out in different parts, so it can be a bit of a problem. Right, using communities. So basically 2 things we're going to look at here, RFC 1998 usage, and then generally what ISPs around the internet are doing. This again is all for multi-homing. RFC 1998, it's written by Tony Bates and I think it was Enka Chen when they were at MCI. Describes how to implement load sharing and backup on multiple inter-AS links using BGP communities, basically. The idea was to simplify life inside MCI and give more control to the customer. And again, when the RFC came out, we implemented it in UUNet, and we basically just handed off everything to the customer. The customer wanted to do something with the load sharing, we said, well, do this. They didn't have to phone us up every day and want immediate changes, as a lot of them seem to want to do that. It simplified upstream configuration, and it simplifies network operation. The support people aren't forever taking phone calls, which say, please change this, please tweak that, please whatever. Right? As I said, give the customer a rope. They can hang themselves if they want. Right. These 4 community values were defined in the RFC. Your AS number, :100, basically set local preference 100, became the preferred path. If we had this community, the AS number 90, we set local preference 90, and it meant it was the backup route if you're dual homed on that AS. 18 meant the main link is to another ISP with the same AS path length, and 70 means the main link is to another ISP. That's what the RFC was about. Now the customer router configuration, as I mentioned at the start, if you're using templates to build all your customer router configurations, whether you give them samples or whether you offer a managed router service, it becomes really easy to configure all this. You just produce this template and just drop in the IP addresses as you need. Okay, so this is the peering with the backup ISP. We send the community, and then on the route map outbound, we set a policy, config community. Because this is the backup ISP, we're going to set, okay, I've got it slightly wrong, but anyway, match AS path 20, so we're matching the local AS and we're setting community 109:90. Okay, so we're sending our upstream 109:90, that is saying this is the backup path. Okay, so rather than sending a metric, some people nowadays saying, well, there's not much point using metrics. It's not helped by different vendors having different values for the default metric. So using community, telling your your upstream ISP, we send you this community. This community means set local preference to 90, which does the same thing as setting the metric. Okay, but just tidier. The ISP router configuration, well, community list 70 does this, 80 does that, 90 does this. and then we set up the route map. This route map is applied to the customer BGP peering. If we get a prefix coming in with community 70 set, in other words this one, we set local preference to 70. So rather than listening to an MED which says this is not really very important at all, we hear the community and set local preference. Okay, and then next slide carries on. If we hear this community, we set that. If we hear this one, 109.90, we set this one, and so forth. Okay, so you just put that on your aggregation router that connects your BGP customers, and it becomes very straightforward. Quite a few ISPs actually support this RFC like this. In fact, most ISPs extend it quite significantly, or they change it slightly to do what they want to do. Certainly in Europe, if you look in the routing registry and RIPE's routing registry, they will list what they do by putting it in the AS object. ISPs here in the US tend to put it on their website, like the network operations website or the customer support website, what communities they actually support. But it's good to actually document somewhere what's going on. Even if you've got, say, RADB or an Aaron's routing registry, you have your AS object there. If you simply list for community policy or multi-homing policies and a URL, that's actually quite useful. Now, just some configuration examples so you can see what's happening. Here's the same one as before. Few links to the same ISP. This one's the primary path, that's the backup. Before we were using local preference and MEDs. Okay. This time around, we're going to use communities. So router A, that's got the primary path. That's the same configuration as before. Router B is the backup path. And this time we're going to send the community. We're going to send communities to our upstream. Aggregate out, default in. Router D out, router D in. These are the route maps that set the policy. And the policy we're going to set is a community type 1. Match our aggregate. So we send our aggregate out, we set community 109.90. If our upstream hears 109.90, he says, my customer wants me to set local preference 90 on this. This is the backup path. So the prefix arrives at the upstream ISP, local preference 90 goes onto it, and it becomes the backup. Right? So you don't have to rely on MEDs to do this. And you can give the customer this type of control, especially if you offer other type of policy options. It becomes quite easy to do. Of course, inbound, we set local preference 90, and that makes that the backup path as well. Router C, so this is the upstream, the main link, default originate, prefix list as before. Router D. All we need to do is route map BGP customer in. Yes, this example needs a little bit more than at the start of the presentation because the upstream ISP needs this route map to try and deal with all the communities that are coming in from its customers. Right. Given that a lot of people offer a lot more than just RFC 1998, it makes sense to do it this way. Your route map is standard route map. BGP customer in, match community 90, set local preference 90. So if community 109.90 comes in, we set local preference 90 on the prefix. Okay, and I've snipped the rest out. You can read the RFC to get the full example a few slides earlier. Okay, now this one's interesting. Here's some examples I've just simply picked up off the network of what ISPs are doing, what communities are supported. Right, so RFC 1998 is actually is okay for simple multi-home customers. It assumes that the upstreams are interconnected. But it's simple, and there are actually many, many more complex situations that people try and do. So I'll just jump over this. So here's the first example. That doesn't come out very well. Okay. This one is ConnectCom in Australia. This is handcrafted by Mark Pryor, and it's actually quite an interesting policy to have a look at. So Connect basically support these communities. So if you send them this community, they only announce a prefix to domestic rate ASs. This one, they only announce it to the local POP. They don't send it outside. Here we're lowering the local preference So he's used different ones from RFC 1998. This one we announced to non-customers with the no export community. This one announced right over the satellite link only. In Australia we've got satellite as well as undersea cable. So these are the communities he supports, and I've got access to a customer connect, and I certainly played with this to find out what it did, and it's actually quite useful what these all do. So that's one example. Next example, well, UUNet in Europe, and in fact UUNet in the US and UUNet in Asia Pac do all this. If you send them 70280, they set local preference 80, RFC 1998. 702.120, local preference 120. We actually push the local preference higher. Okay? 702.20 only announced to UNet ASs and the customers. 702.30 keep within Europe. And then 702.123 does the prepend 1, 2, and 3 at the edge of UNet's network. Okay? That's UNet's example. Concert. Concert's example is huge. You should have a look at it. If you look up this AS in the RIPE registry, it's huge what they support. I mean, there's no point putting it on the slides. It will take about 30 slides. But you can send them all these different communities, and if you send them this one, 5400:1000, it says, don't announce my prefix to all the European peers. Or 5400:1002, don't announce to EUNet. Or if I send 5400:2002, prepend 5400 when I announce the prefix to EUNet, and so forth. This is a fascinating one. It's really well worked out. And actually, I think it's actually all come from here. Nekomar's community traffic engineering capabilities are quite extensive as well. Again, if you can go to the website, it's the AS3257.net website, you'll find the entire community list that support. You can see the size of the scroll bar there. It's a huge web page of all that they actually support. And this is quite a fascinating list of communities and policies that they support. But that shows you what can be done with BGP communities for multi-homing. Right, several more. Another thing they've got on the web page is they've got all the iOS configuration that they use, which is actually quite good. I think a lot of people are actually just lifting it from that web page and implementing it for their own network. It's worth having a look at. I only discovered this at the RIPE meeting a couple of weeks ago, and I thought, this is fascinating. It's actually really interesting. Somebody's actually sat down and worked quite hard to make this function. Right, case study, and then we can go home. Right, this is the case study. This is the interesting one. One of the ISPs I look after in Asia needed to multi-home. They were connecting to AS5400 in Europe and 2516 in Japan. They've got the 19 address space, they've got the AS number, and they've got the circuits. They want symmetric routing and equal link utilization in and out, as everybody seems to do. International circuits are expensive. Well, in this case, they've got satellite because there's no land link out of the country at all. The two 2600 border routers with 64 megabytes of memory. They can't afford to upgrade memory or hardware on border routers. Gross per capita income is like, I don't know, a night in this hotel on average, something like that. It's like they don't have money. So even buying a 2600 is seriously plundering the coffers. And you get the email saying, please make this work. So that's a picture. Both 1 megabit circuits. What was poor was both the upstream ISPs basically refused to talk to them because they didn't have a router that could support the full routing table. And they were a bit perplexed because that basically meant something like a 3660, which they weren't really prepared to go they couldn't go and spend money on. And the simple solution is accept the default from one upstream and partial prefixes from another. That's the one that I've used for years. So why it couldn't be used here was, I don't know. And the first cut at setting this up, well, I just went to some of the looking glasses. Several looking glasses. I just started off with the user one nitrous Digex net, started there. Check the AS path to 5400, check the AS path to 2516. I went East Coast, US, went West Coast, US, somewhere in the middle as well, forget. And I found that AS2516 was in general one hop closer to where I wanted to be. So trying to define the center of the internet is hard. So I just went, some of the looking glass in the US, and I found that 2516 was one hop closer. So my solution is, right, to make them look the same length from the center of the internet, I do an AS path prepend of 1 on the AS2516 peering. So outbound announcement of the 19 to 2516, I did a prepend of 1. To 5400, I left it alone. Whoa, okay. So I thought, well, that's a first cut. Amazingly enough, that was all I needed to do. I mean, that just worked. I was really, really surprised. And on average, I was seeing about 600 kbits per second inbound on the two circuits. All right. The thing is, it did vary according to time of day. This is something I'm going to have to go back and have a look at, because the circuit to Japan was busy in the morning, inbound. The circuit to Europe was busy in the afternoon, inbound. And that's like, I can't see any reason why that would be. I mean, it just seems bizarre. But it worked. It was about the same. Outbound load sharing, well, that was harder. First cut, well, I requested default from 2516, so they sent the full routing table plus the default. And I said, no, just the default, I don't want the full routing table. And they were a bit puzzled, but they quite happily gave it to me. Requested the full routes from 5400, well, that's all they could do. And then I looked at my routing report. Okay, this is a bit bizarre, but this amazingly enough worked as well. I picked the top 5 ASs that are contributing to the routing table and created a filter list. So these were the top 5. And basically, all prefixes originated or having gone through those ASs, I threw away. It was actually a significant chunk of the routing table, about 70,000 prefixes. Okay. I allowed prefixes originated by 5400 and up to 2 hops away, though. That gave me about 32,000 prefixes. Okay. Wasn't very good. I was seeing a lot more outbound traffic on the 5400 path to Europe than I was seeing in the path to Japan. And it was very asymmetric traffic as well. We'd go out through Europe and come back, go out through Japan, come back in through Europe, which was not quite what I wanted. So I just added the next 3 S's from the top 20 lists, so 209, 2914, and 3549. If they appeared in the AS path, I threw those prefixes away as well. Moved it down to 14,000. Traffic was now evenly load shared, about 200 kbits per second outbound on average. And the amazing thing is, it's symmetric. I tried many sites, many of the popular sites that they look at. I just had to look at some of the net flow statistics for the popular sites, and the traffic was symmetric, which was, I don't know whether it's an amazing stroke of luck or just how it happens, but it just worked. And the configuration we had, well, on the first router, we're using OSPF as the IGP. We set metric 20 for default BGP configurations on here. So the peering was like this: remote AS, eBGP multi-hop, update source, blah, blah, blah. Prefix list in, filter in. We're getting the full routing table, so we threw away the private addresses, if any were sent. Out filter, just the /19. Filter list 1 in, filter list 3 out. And then the static default pointing to the serial interface. This static default makes the default originate work in OSPF. You need that. And here was access list 1 AS path. So I threw away all prefixes that had been through these, 8 ASs. These are like the top 8 ISPs in Tony Bates' CIDR report or my routing report, whichever you want to look at. I allowed all the prefixes that come from 5400, 5400's neighbors, and their neighbors, and threw away everything else. Okay? So that gave me about 14,000 prefixes. For outbound, I just allow, don't believe it, I've killed 2 pointers. I have. Okay. Right, okay, outbound we just allow the local AS. And then router B, we have default information originate. This default metric I think is 10. So this became the primary path. And then the BGP configuration, we've got the neighbor, They don't support route refresh, so I have to do the soft reconfiguration. The prefix list accepted just the default route from them. But if I somehow broke this configuration, then I had a maximum prefix command to put on there as well. And I still have a filter list 2 in, and all just for the default route. Outbound, the same out filter, and then filter list 3 out. All that just to take the default route. A lot of safety belts here. Okay. This one I don't need, I mean it's not doing anything, it's saying only accept prefixes from 2516. It's only going to send me the default anyway, so this is surplus. But I've got three safety belts there. Outbound, I just did the prepend, one-time prepend. Okay? And that was it. It worked. Here's the full routing table, throws away most of it, because we could either get full routing table or no BGP. We wanted BGP, so that's the way we do it. Static default points to the serial interface. If the link goes down, the OSPF default is removed, and then router B becomes the main link. And the failover for this is actually about 15-20 seconds, so it works very well. Router B, here's the default from 2516. If the default disappears, in other words, the BGP goes down, the link goes down, the OSPF default is removed, and that one becomes the primary path. Okay. MRTG graph, just to prove, they're virtually symmetric. That's just picked at random a few weeks ago, but it actually works pretty well. I mean, it's about 300, 400 kbits per second here at this stage. It's roughly the same there. The profile is different on the links at different times of the day, which is the fascinating bit. Okay. Multihoming is not really that hard, I don't think. It does need a bit of thought, a bit of planning, in the ways I'm suggesting you should try and do it. The case study is actually a pretty good strategy. I follow that one in each one that I'm working with, try and set up. And this is one that's working really, really well. And the guys, they know very little about BGP, but they can understand what's happened with this configuration. It's actually quite straightforward. And the thing is, we've done this with a 2600. It's like a long-in-the-tooth 2600, one of the first ones that came out. And it's working very, very well, right? And we tell the two upstreams, like, but you can't run BGP on a 2600. It's like, it works. And, the failover, I mentioned the failover being 15 seconds deliberately. If you're carrying a full routing table for 2 feeds like this, do you get 15-second failover? You don't. Okay. Quick summary, keep it simple. Full routing table rarely required. If you want 109,000 prefixes, this will make Sean Duran happy. Charge them money for it. Quite seriously. I know it's not popular, but do you really, if you want to carry 109,000 prefixes, you've got to go and buy really, really expensive memory. Pass the cost on. Anyway, that's it. Thank you for waiting longer. Yes?
You said 5 cents of memory. It's not the memory, it's the router that won't take it. 7206's largest processor is the one that goes to 512.
Yeah.
You can kill it from a cold start for under $100.
Yeah.
Make it smaller for under $100.
Yeah.
Arrogant, obsolescent engineering, whatever you want to call it, but they don't make the things to take more memory.
That's right. Yeah. I agree. It's been a bugbear for me for years, but it's, yeah.